out today. You should have access to your scores online. I posted them. If you can't see it, let me know. So, excuse me. Okay. So if you can't see them, let me know. Approximately 20% of the people got an A. About 25% of the people got an F, and about 30-something got a C. And there were a good number of Bs and not so many Ds. So it was a trinomial distribution centered around A, B, and C. So if you didn't get an A or you didn't get an F, you probably got a C and vice versa. All right. So let's continue. We're on chapter 2. And you guys are going to have another quiz coming up soon, and I'll say a little bit more about that. Okay. So the outline of this chapter is going to start off with describing functions. Okay, we read past that. We're in one. Okay, so the second part of the section, which is going to focus on the first and second derivative, right? So what did we talk about in the last section? What we spoke about in the last section is we looked about when is a function increasing. We talked about where is the function decreasing. We talked about what it meant for something to be concave up. We talked about what it meant for something to be concave down. Okay? So what do these have in relation? Well, we talked a little bit about what the relationship was. The relationship essentially said that if your derivative is positive, for your function should be going up or down. Can someone tell me? Up, right. If the function is negative, should the function going up or down? Down. What if the derivative is 0? If the derivative is 0, your function is not going up or down. Okay? The second derivative you're going to see is related to concavity. When the second derivative is positive, you're going to have a bowl shape up. When the second derivative is negative, it's going to be a bowl shape down. Now, if the first derivative and the second derivative are negative, it does not mean your function is negative. It just means your function is going down. If your second derivative is negative, it does not mean your first derivative is negative. Okay? So this can be a common point of confusion, and we're going to see some examples. All right. The first derivative rule. This is what we just said. If the function evaluated at a point A is greater than 0, then f of x is increasing at A. Okay? So if this first figure over here, if this function is going up, that means the tangent line on any point of the curve has a positive slope. So this function is increasing. That means at this point A means two things. Either you can say the function is increasing, or the slope of the tangent line at that point is a positive number. When the function is decreasing, if the derivative at a point A is decreasing, it tells you that the function is going down at this point. Or if we draw a tangent line at that point, that the slope of the tangent line is negative. Okay, so we're going to use an example, the first derivative. Sketch the graph of a function that has three properties described. F prime of 1 is negative 1 equals 0. All right, so this is going to mean that the function at negative 1 crosses the x-axis. It's going to mean that the function, when it's less than 0, is doing what? So f prime of x is less than 0. What does that mean if we're less than 0? Okay. So the function f prime of x is less than 0 means what? If the function is less than 0, what does that mean? Decreasing. Right. So the function is decreasing when x is less than negative 1. F prime of negative 1 equals 0. So at negative 1, is the function increasing or decreasing? Neither. Right. So f prime of negative 1 equals 0. That means the function is neither increasing or decreasing at 0. F prime of x is greater than 0 for x is greater than negative 1. So if we're greater than negative 1, is the function increasing, decreasing, or neither? Increasing, right. F prime of x is greater than 0 means the function is increasing. When is it increase? When is this true? When x is greater than negative 1. So here's what the function is going to do. At negative 1, the value of the function is 0. If we're less than negative 1, the function is decreasing. If we're greater than negative 1, the function is increasing. Before I draw the picture for you guys, anyone have an idea of what it's going to shape like? The function's 0 at negative 1. If we're to the left of negative 1, the function's going down. Once we get to negative 1, the derivative is 0, so it flattens out. Then when we get bigger than negative 1, the function's going up again. So if we're less than negative, if the function is 0 at negative 1, if we're less than negative 1, then the derivative is 0, so we're decreasing. At negative 1, the derivative is 0, so it's a flat line at 0. And f prime of x is greater than 0 for greater than negative 1. Okay, if no one can tell me the shape, if you had to choose between concave up and concave down, what would it be? Concave up, very good. Right? Because we're going down. So let's draw these. Okay. Okay, so we have our conditions here, and our conditions are that f of negative 1 is equal to 0. This means the actual function has a value of 0 at negative 1. We know that the derivative of x is less than 0. That means the function is decreasing when x is less than negative 1. So whenever we're less than negative 1, the derivative is 0, so it means the function is decreasing. We know that f prime of negative 1 is equal to 0, right? X is equal to negative 1. That's what that means. And we have one last condition, and that is the derivative is positive or increasing when or greater than 0. This f prime of x greater than 0 means increasing when x is greater than negative 1. So if we draw with each of these conditions, we know that f of negative 1 equals 0. So this is 0, and the function, f of negative 1 equals 0. So if I go out to negative 1, this value of the function is 0 over here. Now, if I'm less than 0, is the function going up or down? Down, right? So if we're to the left of 0, approaching negative 1, the function is decreasing. Now, at negative 1, the derivative is 0, so it's going to be a little flat at negative 1. That's what it means. For the derivative to be 0, it just means the tangent line is a horizontal line. So it's going to flatten out, give us a horizontal tangent line at negative 1. And once we get bigger than negative 1, what is the function doing now? Increasing. If x is greater than negative 1, f prime of x is greater than 0. And the function is going to be look something like this. And of course, it's concave up. It has a bowl shape. The formal definition of concave up means if we draw a tangent line on any point in the concave region, the tangent line is below the curve, right? So if I draw the tangent line at 0, it's below the curve. If I draw a tangent line like here, it lies below the curve. The intuitive way to think about that is that it's shaped like a bowl. Concave up means it's bowl-shaped, right? It looks like a mixing bowl or something. You can pour something in it. The mathematical definition, obviously, if we're trying to describe something mathematically, we can't say it looks like a bowl, write an equation for it. We say that the tangent line lies beneath the curve at all the points. The tangent line here is below the curve. This tangent line is below the curve. This tangent line is below the curve. That's what concave up means. Concave down means the opposite. Concave down, as we discussed last time, if I have this curve over here, and I draw a tangent line up here, the curve is below the tangent line. If I draw a line over here like this, the curve is beneath the tangent line. If I draw a curve like this, the curve is again beneath the tangent line. That's concave down. Intuitively what it means you have a hill, or an upside down bowl. Concave down. You can think of the hill going down or something. Concave up means you have a bowl-shaped region facing up. Mathematically, for concave down, every point on the curve is below its tangent line. Mathematically, what does concave up mean? Mathematically, concave up means that every point on the curve is above its tangent line. This point over here has this tangent line. This point over here has this tangent line. Okay? So if we go back to our graph, they're going to give us the same spiel that we just talked about, and they wind up with a curve that looks like the one we have. Derivative is negative if we're less than -1. It's decreasing at 0 at -1, and then it starts increasing. Second derivative rule. Second derivative rule is just a quick way to tell if something's concave up or concave down. Now, not all functions that are concave up have a second derivative, right? So, but in this class, generally everything we're going to do is going to have first and second and thirds and as many derivatives as you want. But sometimes the functions we're interested in, whether it be in finance, especially in finance, things get really messy from a mathematical point of view. Actually, I think one of Black-Scholes equation, how many people are familiar with Black-Scholes equation? It's the formula used for option pricing. I think someone won a Nobel Prize with that. It was basically just a simple application of stochastic calculus. The calculus is extremely complicated, though. But applied in the right way, I guess you do something good. But they use that for option pricing and so forth. But second derivative rule. If the second derivative of a function is greater than 0, then it's concave up at that point A. So if f prime of A is greater than 0, then it's concave up at that point. If the second derivative is less than 0, then it's going to be concave down at that point. Okay? So an example of that is, before we go on to the next slide, suppose we have the function I'm going to draw a picture first. Right? Now, if we have a function that looks like this, all right, and you can think of this as a decelerating vehicle, right? Because the steeper if this is distance and this is time, the steeper the tangent line, that's the velocity, first derivative, the faster it's going. But you can see the tangent lines are getting less steep as we continue. They start out very steep and they're slowing down. So look at this. Is the first derivative of this function positive or negative? How do you know that? It's going up. If it were negative, the function would be going down. Is the second derivative positive or negative? How do you know? Right. That's definitely right. That's one way to say it. It's got a bowl shape, right? It's starting to form into a bowl shape. Or if you draw any tangent line, the curve lies beneath the tangent line. So if I pick this point over here, and I draw the tangent line at that point, the curve is beneath the tangent line over here. So it's concave down. And that's the other way to look at it, is the derivative negative is a concave down. Also, the derivative is going down. Let me just redraw that. I'm running out of paper space over there. Over on this curve, the first derivative is positive because it's going up, or as the guy in the second row over here said, the second derivative is negative because the derivative is getting less steep, so the derivative is going down. That's a really steep derivative, but this derivative is almost zero. This tangent line has slope almost zero. This tangent line has a strong positive slope. So what's going on is the second derivative the first derivative is decreasing, which means that the second derivative is negative. Okay? And you're going to see all this again. Good to take notes, watch the video. But also, what about a function that looks like this? Is the first derivative negative or positive? How do you know? It's going up. The function is going up. Is the second derivative negative or positive? How do you know? Yeah, it's bowl-shaped up. You can also look at the tangent line at a point, and you can say the tangent line lies beneath the curve at that point. You could also look at the steepness of the tangent. The tangent lines are getting more steep. If the tangent lines are getting more steep, that means the derivative is going up, which means the second derivative is positive. Okay? So just some things to think about. Let me do a couple more. So if I do a couple more of these, suppose we have a function that looks like this. Okay? Suppose we have a function that looks like this. Now, is the first derivative negative or positive? It's negative, right? Because the function is decreasing. Is the second derivative negative or positive? Raise your hand if you think it's positive. Raise your hand if you think it's negative. So tell me, is this bowl-shaped up or bowl-shaped down? So is this bowl-shaped up or bowl-shaped down? And if it's bowl-shaped up, what does that mean? Positive, right? And the derivatives tell you that too. If I draw a tangent line right here, is that the slope of that line negative or positive? If I draw this line right here, that tangent line, is that negative or positive? Negative. If I draw the tangent line right here, that's about zero, right? So we went from a negative first derivative to a zero first derivative. So the second derivative is positive is a way to think about that. Or we can just look and say, well, that's concave up, and that's good enough, right? Okay. So those are just some examples. So the first and second derivatives really, really help us graph these functions. Okay? So let's go back to okay. So if f prime of a is greater than 0, the function is concave up. Concave up means the tangent lines are always beneath the curve in that region. Concave down means in your concave down region, the tangent lines always lie below the curve. I mean above the curve when it's concave down. Any questions on what I just did? Okay. Now here's some of the pictures I just drew, right? So I just went through some of these. For this function, it's bowl-shaped up, so the second derivative is positive, it's increasing, so the first derivative is also positive. This one is increasing, so the first derivative is positive, but the slopes of the tangent lines are leveling off, so the second derivative is negative, or you can think about this curve as a decelerating vehicle, right? If you're driving your car and you start applying your brakes, distance over time looks something kind of like this. You're still going up, but the rate at which you're going up is kind of leveling off. This one, the function is decreasing, so the first derivative is negative, but it's bowl-shaped up, so your second derivative is positive. You can also see, if you think about this as distance over time, you're accelerating. Over here, you have your derivative is negative, means you're going backwards. It looks like you're going to level out to 0 here at some point, and you're going to start moving forward. So in this example, your second derivative is positive, means it's bowl-shaped up. You're also accelerating because you're going the wrong direction, Okay, now you get your speed to 0, and then you're going to probably start going up, hopefully, in the right direction. And over here is the function decreasing or increasing. So is the first derivative negative or positive? Negative. And is it getting more negative as we go forward or less negative? So what's the second derivative? Negative, right? The rate at which you're going in the wrong direction is increasing. Right? You're going to get really lost. Okay. Sketch the graph of a function that has the properties described. Okay? So what we want here is we want f of x is only defined at x greater than 0. Right? So f of x is only defined for x greater than 0. We have the points 0, 0, and 5, 6 on the graph. F prime of x is greater than 0. F of x is, for x greater than 0, it's going to, okay, so we see all the conditions. So let's start at the beginning. So the function is 0 at 0, right? This is just a point on the graph. I mean, that's really nothing for the shape. We can always fix that after. The function is, so if we're greater than 0, is the function going up or down? Up, right? So at 0, okay, so the function starts at 0. The value of the function at 0 is 0. 5, 6 is on the graph. I mean, that's not so important. We want to get the shape first. We can fix the points later. Once we're greater than 0, f prime of x is greater than 0. So what is the function doing when we're greater than 0? Going up. Now, f prime of x is less than 0, is negative when we're less than 5. So what is the function concave up or concave down when we're less than 5? Concave down. F double prime at 5 is equal to 0. We don't have any rules for that yet. We did see that in 2.1, but just a reminder, the function, when the second derivative is equal to 0, it's usually going to mean that the function is going from concave down to concave up for x greater than 5. Okay? So let's draw this. So when you're doing these, you know the rules, so you kind of guess about what it looks like when you go back to your conditions and saying, is this what I was trying to draw? Okay? So when you're doing these, the concept's pretty simple. This means it's up, this means it's concave. But when they ask you to draw them with all these points in it, well, how do you proceed? You kind of guess. You just kind of guess and say, well, it's going to be going up here. When you're done drawing it, you go back and say, is it increasing where it's supposed to be increasing? Is it decreasing where it's supposed to be decreasing? Is it concave up where it's supposed to be concave up? So how do you approach these problems? You kind of guess at it, and you go from there. Okay? So let's okay. So let's go. Let's try drawing this. All right. So the function, the properties of this function again are that f of x is only defined for x greater than or equal to 0. That means we're only in the first plot, we're only on the positive x-axis. We're not going to consider negative values. The next criteria that we have is that 0, 0 and 5, 6 are points on the graph. Another way to say that is f of 0 is equal to 0 and f of 5 equals 6. Very good. The next thing that we're going to say is that f prime of x is greater than 0 for x greater than 0. So if we're greater than 0, what's the function doing? It's going up. Okay? So we have f prime of x is greater than 0 for x is greater than equal to 0. So that means the function is only defined greater than equal to 0. So that means as long as we're greater than 0, the function is going up. And we have some conditions about concavity here. So we know that f double prime of x is less than 0 for x less than 5. We know that the second derivative at 5 is equal to 0. And we know that f double prime of x is greater than 0 for x greater than 5. Okay, before we draw this, this tells us just where the first one tells us where the function is defined. Right? So we're plotting on the positive direct axis. So the first one is where it's defined. The second one is just some points on the graph that we're going to plot. Now, this condition over here, what does this tell us? F prime of x is greater than 0 for x greater than equal to 0. But we only define the function at these points. So is the function going up for all x or down for all x or neither, or what's going on here? Going up. So this tells us the function is always increasing. Now we have something going on at 5. If x is less than 5, is the function concave up or concave down? Down. So these three are concavity. Okay? So these last two are concavity. F double prime of 5 equals 0 means it's not concave up or concave down. Because if it's less than 0, then it's concave up, concave down. If it's greater than 0, it's concave up. If it equals 0, then it's neither. And what that'll turn out to be is usually something called an inflection point. It's where we go from concave up to concave down. Doesn't have to be, but that's generally what it means. All right? And so this means concave down. What does this last one mean? Concave up. Okay, so let's draw this. Now, the way I wrote it down here, it's going to be very easy to draw. The concept is simple, but that doesn't mean the problems are untricky, right? Because you see there's a lot of information here. The more you do it, the better you get. The concept is simple. The problems can be confusing. There's a lot of information here. How do I draw this? Well, the way I started doing it is I just guess. Then I go back. I kind of look at it. I kind of give an idea of what I want it to look like. You know, I put my points down. And I go and I see, okay, does this make any sense? I check my conditions. If not, I adjust it a little bit. So, but here's how we're going to do it. We'll start with the beginning. We have 2 points on the graph. What's the value of the function at 0? Right? And if I go out to 5, 1, 2, 3, 4, 5, what's the value of the function at 5? 6. So go 1, 2, 3, 4, 5, 6. and I have the point 5 comma 6. Now, what is the function doing between 0 and 5? Is it increasing or decreasing? Increasing. Is it concave up or concave down? So, let me see. If we're greater than 0, okay, you're right, concave down. So, the function is always increasing. The first derivative is always positive, but if we're less than 5, it's concave down. So it's going to be bowl-shaped up or bowl-shaped down between 0 and 5? Down, right? The function's increasing. The bowl shape is an upside-down bowl because the second derivative is less than 0 and we're less than 5. So the function is going to have to look something like this. But when I get to 5 and 6, what happens when I'm greater than 5 now? We're still increasing, but if x is greater than 5, the second derivative is positive, which means it's bowl-shaped up. So what happened is, think about this, it's like you're approaching a stoplight, you throw your brakes on, you're slowing down, but then like the people behind you want you to get going, so they don't miss the light. So you put your foot on the accelerator, and you do something like this. Maybe not the best picture. This over here is where the second derivative is 0, and often that's going to be an inflection point. Not always, but when you're checking for inflection points where the second derivative is 0, and that's where you go from concave down to concave up. All right? Any questions on that? Okay, let's go back to their slide and let's see how they draw it. This is just a spiel. I'll send the slides to everyone if someone wants to send me an email if you want to look at what they said. But basically they're saying the same thing I said, and they will end up with a much prettier graph than mine. But their concavity is not as well pronounced. The point 5,6 is on the graph. This is bowl-shaped down. It's not a very steep bowl. And this is bowl-shaped up over here. Their bowls are not as pronounced. It doesn't have to be. Okay, let's look at another example. We have 3 functions here. We have the first derivative, the second derivative, and the third derivative. We're going to use all 3 to explain why this graph has a minimum at x equals 10, a local minimum. So does someone remember what the intuitive idea of a local minimum is? The what? Yeah, you're right. It's the bottom of a hill, right? So mathematically what it means is that there's a region, if you take the point 10, that's where they're saying it's a local minimum. It's a local minimum if there's a region around that point where it's the lowest point in the region. Okay? So the function is what's in blue. F prime of x is the original function, it's what's in blue. And to be a local minimum, or a relative minimum, it means you're at the bottom of a hill. It also means that it's the lowest point between some range of x values. Like if it doesn't matter how small you make it, and that's why the mathematical definition you need to think about a little bit. But what it means intuitively is that it's the lowest point of a hill. A valley, I should say. I'm sorry, a valley, not a hill. Okay? So let's look at what happens for the first derivative. So the first derivative is the line in red. So let's look to the left of 10. Do you see? Everyone see where I have the mouse pointed? Does everyone see? Where I have the mouse is the derivative negative or positive? Negative. So in this region is the function going up or down? It's going up. So forget about the picture. Think about the definition. You know that the second derivative is negative here, right? What does it mean the function is doing if the first derivative is negative? Going down. And look it. That's what I said in the class. When you want to know if the function, if you have a graph of the derivative and you want to know what the function is doing, you say, well, the derivative is negative here, so it means the actual function is decreasing. You guys see that? The derivative is negative, the function is decreasing. The shape of it just tells you how fast and how slow. Okay? But the derivative is negative, the function is decreasing. So if we just look at the graph of the first derivative is decreasing and decreasing and decreasing and decreasing. Even though the first derivative is going up, the function is still decreasing. But what is the value of the derivative at 10? 0. So at this point, is the function going up, down, or neither? Neither. Now what happens as we move to the right of 10? What's the function doing? Increasing. That tells us we have a relative minimum. Why? Because the function is decreasing and decreasing and decreasing and decreasing. Levels off, first derivative is 0 here. After this value, we're on the positive x-axis, and that tells us that the function is increasing, right? So if we look at the graph of the derivative, it's negative here, it means the function is decreasing, the function is decreasing. The function is decreasing. The function is decreasing. It is accelerating, which is good. So so we're gonna try and go in the right direction here. The function is decreasing. The function is decreasing. The function is no longer decreasing at 10. It leveled off. The derivative is 0. When the derivative is positive, it means the function is increasing. The function is increasing. The function is increasing. So why do we have a relative minimum here? Because we're decreasing till we get to 10, we level off, and then we go up again. So we have an explanation for why this is a local minimum looking at the function. We have an explanation for why it's a relative minimum looking at the first derivative. Now what we're going to do is we're going to look at the second derivative. Now the second derivative is a straight line. It still tells us information about the function. So if we look at the second derivative, right? The second derivative is going to be okay. So if we're in this region over here, if we're in this region over here, what is is it concave up or concave down? So if we're less than 6, down. So that means if you look at over here, the function is concave down. If we're from 0 to 6, the function is bowl-shaped down. When we get to 6, what is the value of the second derivative? And what can we have when the second derivative is 0? Flexion point. So look, if we look at 6 and we go back up here, the function is bowl-shaped down over here, but when we get to 6, it's starting to be bowl-shaped up. Right? Now the second derivative is not going to be enough to tell us if we have a max or a min, but it's going to help us out greatly. Okay, so because we're going to see if we look at points where the first derivative is 0, and if the second derivative is positive at that point, right, then that's going to be a minimum or a relative minimum. We're also going to see if the derivative is 0 at some point and the second derivative is negative, that's going to give us a maximum. Okay? So this slide is just to give you an idea of how all three are related, but we're going to have a theorem in a second that's going to say if the first derivative is 0, and look, the first derivative is 0 at 10, and the second derivative is positive, we're going to wind up at the bottom of the hill. Right? Because what it means, the second derivative being positive means we're concave up. The first derivative being positive, the first derivative being 0 means that we have a flat line at the bottom, so it means we're at the bottom of the hill. So if the second derivative is positive and the first derivative is 0, we have a bowl-shaped up, it means we have a relative minimum. If the second derivative is negative, means bowl-shaped down, and the first derivative is 0, means we're at a flat point, means we're at the top of the hill, and that's a relative maximum. Now over here is exactly the same thing we were just saying. And actually, before I go on to this next slide, let me just redraw that for you guys. Okay? So whenever we have a graph like the one we just had, okay? And we have a bowl over here. What is the second derivative for this function? Positive or negative? Positive. Right? Now notice that where the first derivative is 0, right? If we're to the left of this point over here, let's say this is 10. If we're to the left of 10, is the derivative negative or positive? Negative, the function is decreasing. If we're to the right of 10, is the derivative negative or positive? Positive. What is the value of the derivative at 10? 0. So look it. When it's 0, we have a flat line. It means so it means if we have a concave up region, then where the derivative is 0, we have a relative minimum because it's like sitting a bowl on the table. The table represents the tangent line for this value 10 over here. It's flat. It's at the bottom of the bowl or the valley, however you want to think about it, because everything around it is concave up. Similarly, if we have this function over here, say this is 10 again, what is the derivative at 10? What is the derivative at 10? So, what is the derivative to the left of 10? Positive. What is the derivative to the right of 10? Negative. See how we're increasing then decreasing? Derivative is negative here. What is the derivative at 10? 0. It's flat. So in this case, is 10 a relative maximum or minimum? Maximum. It's a bowl shape down. And notice the top of the bowl. So if you have, first of all, it also is the second derivative positive or negative here? Negative. It's bowl shaped down, the second derivative is negative. So if you have a bowl shaped region, right, or if the second derivative is negative, you have an upside down bowl shaped region or a hill shape, however you want to think about it, the top of the hill is where it's flat. That's where the first derivative is 0. So if the first derivative is 0 and the second derivative at that point is negative, it's a relative maximum. You're at the top of the hill. If the first derivative is 0 at a point, and the second derivative is positive, you're at the bottom of the hill, and you have maximum or minimum? Minimum, right? Okay, that's the picture we just did. All right. Okay. So let's come back. Now let's look at this picture. Now they're throwing they want to constrain us a little bit. They're taking some information away. After a drug is, because they're not giving us the function. They're just giving us the first and second derivative. Now calculus is really great that with a little bit of information we can go through a lot of stuff. So let's think about this. After a drug is taken orally, the amount of drug in the bloodstream after T hours is f of T units. So the y-axis is how many units of blood are in your bloodstream of the drug. And the t-axis, which is usually our x-axis, is time. All right. Now, we don't have the function. We don't have the function here. All we have is the first and second derivative. All right? So, let's look at this function over here. This is going to be 2. If we're to the left of 2, is the second derivative positive or negative? Well, okay, what's the function of the value at 1.5? The function, if we go to 1.5 on the t-axis, we go up to our curve, and we go to the left, that's a 4. Is 4 negative or positive? Positive. So, is the value of the function, if we're less than 2, the first derivative is positive, right? These are all positive values. So if we're less than 2, is the function increasing or decreasing? So is the derivative positive or negative here? This is f prime of x, not f. Okay, so let's take a So does everyone agree that this blue line is not the function? This is the graph of the derivative of x. Does everyone agree with that? Yes. This is the value 2. Does everyone agree with this? Okay, if we're to the left of 2, are these values, I understand that these values are decreasing, which would indicate that the second derivative is negative, but are these actual values positive or negative? Positive. If these values are positive, what does that tell you about the original function? It's increasing. So just because the derivative is going down, right? All that just tells you about the second derivative. The fact that these are positive values means that the function is increasing till we get to 2. Now, what happens at 2? It's 0. And it's 0. Then after 2, what is the function doing? It's what? It's decreasing. It's decreasing. It's decreasing, right? Okay. So that's going to tell us what the function is doing as far as when it's going up and down. The function is increasing until we get to 2. Once we get to 2, the function is going to be decreasing. All right? So that's going to tell us the function increases until it gets to 2. The derivative is negative all after that, so then the function is decreasing. All right? So that's going to tell us how the function is going up and it's going down. The next thing we need to do is look at the concavity. Okay? So, and again, we're going to do this we're going to do some guessing. So the function is concave up. Okay, so 4 is where the second derivative crosses the x-axis. So is the function concave up or concave down over to the left of 4? Right. The second derivative is negative if we're less than 4. So the function is concave down here. At 4, what is the value of the second derivative? 0. And once we're bigger than 0, what is the function doing? What? The function, the second derivative doesn't tell us increasing or decreasing, it tells us concave up, concave down. So if we're bigger than 4, concave up. So what do we know? And we're just going to guess. We're just going to draw a picture of what we think it should look like. Then we're going to go back to our conditions. And then what we're going to do is we're going to draw it. And we're going to say, okay, does this function I drew look like the one being described? And hopefully yes, and we're done. Okay. So let's do this. And we'll go back over here. Well, first let's write down the conditions. So the first thing I'm going to write down on the paper, and I'm going to write them down as we're going over them. So I know that f prime of x is greater than 0 if x is less than 2. I know that f prime of 2 is equal to 0, right? So that just means it levels off. And I know that f prime of x is less than 0 when x is what? Greater than 2. Okay, now I look at my second derivative. In my second derivative, if we know that f double prime of x is less than 0 for what values of x? So the red graph. F double prime of x is less than 0 for what values of x? Right, if we're less than 4, the second derivative is negative. So for x less than 4. Now, we know that f double prime of x is equal 0 where? 4. f double prime of 0 equals 0, and f double prime of x is greater than 0 if what? Right. So if we look at our second derivative, this is 4. The second derivative is greater than 0 when we're greater than 4, because this is 0 for the second derivative, now we're greater than 0. Okay, so now we have our conditions written down. Let's draw it. Okay? So these are our conditions. Now we're going to draw our points over here. So it should be a 2, I think, right? That should be a 2, I think, right? Okay, so the only points they give us information about are 2 and 4. So I'm going to put a 2 here. I'm going to put a 4 here. All right? Now, if we're less than 2, what is the function doing? So if we're less than 2, what is the function doing? It's increasing. So to where, I don't know, but I just know it's increasing. So it's going to go something like this. All right. And do I have the concavity right? Well, if we're less than 4, which we are, we know that the second derivative is negative. So is what I drew okay? It is? Okay. So, all right. So now what we're going to want to have over here is that if we're greater than 2, if we're greater than 2, is the function going up or down? Down, right? And if we're less than 4 still, we're still concave negative, right? So I'm going to make it still concave down, we're decreasing. Right? Now, if we're greater than 2, we're still decreasing, but what's the second derivative at 4? 0. And what about when we're greater than 4? Well, second derivative, when x is greater than 4, the second derivative is concave up, so what does that mean? Is it bowl-shaped up or bowl-shaped down? Raise your hand for bowl-shaped up. Raise your hand for bowl-shaped down. It's bowl-shaped up. Very good, right? Okay, it's going to look something like this. This just takes a little bit of practice getting used to. There's a lot of things juggling your head. But let's look at this. One function that looks something like this is, well, sine curve, if you've taken trig, but okay. So let's look and see if we drew it right. If we're less than 2, the first derivative is positive, so if we're less than 2, we're increasing. So you can check that. It should be going up, or you can draw tangent lines. They should all be positive. F prime of 2 is 0. That means we're at the top of a hill, or we can just draw a flat line for the tangent line at 2. If we're less than 2, it means that, if x is greater than 2, that means f prime of x is less than 0. It means what? Increasing. Is the function decreasing? Right? Forever and ever and ever, if we're greater than 2, we're always decreasing. Let's see if so we have the first derivative right. We increase till we get to 2, we level off and we decrease. Let's check if we have the concavity right. Okay, so for the concavity, if we're less than 4, are we concave up or concave down? Down, right? So if we see if we're less than 4, we have the concavity right. We should still be decreasing, we are. Now, 4 turns out to be an inflection point, because if we're greater than 4, are we concave up or concave down? Concave up. See, this is a bowl-shaped up region. See, here we're bowl-shaped down, here we're bowl-shaped up. it switches between the two at 4. So this is an example of what this type of curve would look like. The concept is very simple. The problems can be tricky because it gives you all this information. It says draw this. So yes, the concept is very simple. The problems take practice. Okay? Why? Because they give you all this information. You need to organize your information about what's telling you where the function is increasing, what tells you where the function is flat, what tells you what might have an inflection point, what information tells you concavity. So you need to look at what the graph is telling you, break it up like that, try and draw something that you think fits it. Then go to look at your graph and say, is it correct? Check your conditions like I did. And if not, then try and fix it. But, just start out by trying to sketch something that you think makes sense. Then go back and try and fix it. If you've done it as many times as I have, you probably get it right on the first try. And if you do it a lot, you'll just get it right on the first try. But when I first started doing them, I just look at it, sketch something that looks reasonable, and try and fix it. Okay? Okay, here we go. So this is more of just what we've just been doing. We're sketching graphs. Section 2.2 and 2.3 is all graph sketching. All right? Section outline. Curve sketching, critical values. The critical values are essentially going to be where the derivative is 0 or not defined. And why do we care about that? Because if the derivative is 0 and we have concave up, means we have a minimum. If the derivative is 0, means we have a critical point, and the function is concave down, we have a maximum. So this is really important in applications, when you can actually do it. A lot of functions are not nicely behaved, so trying to find a maximum value is tough. But if you had a cost function or a profit function, in terms of units, you might be interested in the production level that gives you your maximum profits, right? So those can be handy things. Or if you might have complicated functions that no one can solve, but you'd love to maximize or minimize. For instance, traveling salesman problem basically says, let's say you have a bunch of airplanes and you have to travel to a bunch of cities. Say you want to find the route that minimizes gas costs, right? If you could figure out how to solve that minimization problem, we won't be doing anything like that. They're called Millennium Problems. I think there's a $7 million prize for it, but the companies would, for that piece of information, would probably pay you a lot more than that. So some problems are easy to minimize, maximize. Some are maybe never be solved. Okay. But when we can take first and second derivatives, we're good. And of course, we're going to be able to do that. Start with f of x and compute. Okay, this is a general procedure. And essentially, it's just more of what we did in the last chapter, except instead of saying, it's exactly what we did in the last chapter. It's just, we're going to beat you over the head with it and maybe add a couple more things. All right. So exactly like I did in the previous problems. If we want to sketch something, we want to know what f prime of x and f double prime of x are. Why? Because if f prime of x is positive, we're going up. If it's negative, we're going down. If it's 0, we're flat at the top of a hill or something. If f prime of x is positive, we're concave up. If f prime of x is negative, we're concave down. So we want to know what these are. Next, we locate all relative maximum, relative minimum points and make a partial sketch. So we're going to see what that is like it was in the last one. The critical points where the derivative is 0 are undefined. And remember, if the derivative is 0, as we saw, and we have concave down, we have a maximum. If the second derivative is positive, and the first derivative is 0, we have a minimum. We also are going to be interested where the second derivative is 0, as we saw that gives us inflection points. And this is exactly what we did. There's nothing new here. We're just beating you over the head with it because it's a lot to take in at once, right? Simple concepts, but there's a lot of little concepts you have to put together to draw stuff. That's what makes it complicated. We're also, in graphing these things, we're going to recall some stuff from algebra because it's still useful. The calculus just tells us what it's shaped like. The stuff like intercepts, like you may remember from an algebra course or such, has to do with intercepts and completing the sketch. Okay? Like, we need to know points on the graph. We need to use a little bit of algebra to draw the graph. Otherwise, we just have a general idea of what it's shaped like. Calculus just gives you a general idea of what it's shaped like. But you actually need some points on the graph if you want the actual graph. Okay? So step 4 is we're going to add some algebra in there because we want to know the actual graph. We don't want to know a general idea of how it's shaped. Calculus just says, is it going up? Is it going down? Is it concave up? Concave down? Well, there's a million different ways you could draw that function. Right? It's nice to know what it's shaped like, but we need to get some points on there. Aha. So just a quick thing. Look at the example real quick. What is the derivative at -1? So here's -1. What is the derivative at this point? Remember from back before the first test, if you have a curve going into a sharp corner, is there a derivative? No. Remember, sharp corners don't work. When you have sharp corners, it's not differentiable at that point. Given a function f of x, a number a in the domain such that either f prime of x equals 0 or f prime is undefined. Those are critical points. Why? Because, well, the second derivative, it has to do with the second derivative. The second derivative can only go from negative to positive at those types of points. Okay? All right. So given a function f of x, a number a in the domain such that either f prime of x equals 0 or f of x is undefined. Okay? So we already have an idea of what the value of this point is in terms of finding maximums or minimums, etc. But whenever I say critical value, it's a term I'm going to be using a lot. So whenever I say critical value, it means the first derivative is either 0 or undefined. All right? That's the first thing that should come into your mind. If I say critical value, it means the first derivative is 0 or undefined at that point. Okay? For the example, for the function below, notice that the slope of the function at 0 is -2, and the slope at 0 at x equals number 2, and the slope undefined at x equals -0.4. Okay? Also notice that the function has a relative minimum and a relative maximum at these points, respectively. Okay. Okay. So let's look at some of these. Can everyone see this okay? All right. So we're going to go back to that first slide in a little bit. I just want to review a couple things on these other slides. The first derivative test. Suppose that f prime of a is equal to 0. Okay, and this is exactly what we talked about. Okay, so first, what we're going to want to do, and we're going to have the second derivative test also, which is going to give us the same information. Okay, so what we're going to basically say is, if we look at a point A, the derivative is 0 there. If we move a little bit to the right, and it's negative, or if we move to a little bit over to the right, and the slope is positive, it means we're going to have a maximum there. Okay? So if we look at the point A, can someone tell me what the derivative at A is? 0. Can someone tell me what the derivative is if we're to the left of A? Right? Does everyone see that? Can someone tell me what the derivative is if we're to the right of A? Negative. So look, A, the derivative is 0. It's a critical point. If we're to the left of A, we're increasing. If we're to the right of A, we're decreasing. We have a bowl shape. So A is a relative maximum. Okay? Now, in a second, we're going to have the second derivative test, which is going to tell us the same thing as this test, a different way. Why do we have both? because sometimes you have a problem and it's really hard to take the second derivative. And so you're going to want to use this. But sometimes it's really easy to take the second derivative, so you're going to use that. Let's look at B. If f prime of x changes from negative to positive at x equals a, the function has a local minimum. So let's look at the graph over here. So what is the derivative at a? So this is the point A. What is the derivative at a? 0. We're at the bottom of the hill, right? Or the top of it's flat over here. We're flat over here, the derivative is 0. It's flat over here also, the derivative is 0. If we're to the left of a, is the derivative negative or positive? If we're to the right of a, is the derivative negative or positive? So if we're to the left of a and the derivative is negative, and we're to the right of a and the derivative is positive, it means we have a local minimum. Or we're going down, we stop at the bottom of the bowl, and we go back up again. So we have a relative minimum. That's what B says over here. C. If f prime does not change sign at a, okay, that is if f prime is either positive on both sides of a or negative on both sides of a, then f has no local extrema at a. Okay, and that's figure C. Figure C and figure D. So here is A. What is the derivative at A? Is it flat? Oops. Is it flat or going at A? Is it flat going up or down? So what should the derivative be if it's flat? 0. If we're to the left of A, is it going up or down? So is the first derivative positive or negative? Positive. Okay, so the first derivative is positive, then 0. And if we're to the right of A, is it positive or negative? Raise your hand if you think it's positive. Raise your hand if you think it's negative. It's positive. So it's positive, 0, then positive. A is not a local minimum or maximum. Okay? Because in a local, you kind of see A is not the bottom of the hill or a top of a hill, or mathematically, there are always points around A that are bigger than it and less than it. So it's not a local. And graph D is just the other case. It's flat over here, so the derivative is 0. But if we're to the left of A, the derivative is negative. It's 0 at A, and to the right, it's negative again. It's not at the bottom of the hill or the top of the hill. It's one way to say it's not a local extrema, maximum or minimum. And the other way to say it is, well, more mathematically, the way you would say it is there are always points around A that are above it, and there are always points that are below it, right? So it doesn't fulfill the definition for a local max and minimum in the purely mathematical sense, which means in some neighborhood, if it's a minimum, there's always all the points are above it, and if it's a local maximum in some region, all the points are below it. But no matter how close you are to A in this picture, there's always points above it and below it. No matter how close you are to A in this picture, there's always points above it and always points below it. In this picture, there's a small region where all the points are above A. In this region, there's a neighborhood where all the points are below A, and that actually is the entire region. All right, find the local maximum, minimum points of this one. So what we're going to do here is we're going to find there's a couple ways we can do this, but all we know is the first derivative. So what we're going to do is we're going to start by taking the first derivative to find the critical points. So we just use the chain, we just use the power rule, and we get f prime of x. Next we're going to set x prime of x equal to 0. And when we set x prime of x equal to 0, we find the critical points. We're going to go through this on paper also, but I just want to walk you through the steps here. We start with the function. In order to use the first derivative test, we have to take the first derivative. We could also use the second derivative test, which we're going to see in a second, and because we can also, remember, tell whether we have a max or a min by whether it's concave up or concave down. right? So why do we have two tests? For some functions, taking the second derivative is a pain. It's a big pain. When it's easy to take, it's the easier of the two tests to use. But when you have sometimes the first derivative doesn't take much work at all. Take the second derivative, you're really taking out the paper there. Really easy to make mistakes, and, no one's happy. All right? So what we do is we're going to use the first derivative test. And what we're going to do is we take the first derivative. The first derivative happens to be this function here, which simplifies to this function here. Now we have a quadratic equation, and the way you solve a quadratic equation is to write in this form over here of ax squared plus bx plus c. You set it equal to 0. You solve it by factoring. Once you factor, you take each of the factors, 9x minus 3, 2x, and 2x plus 1. You set those two factors equal to 0. Okay? Solve for x and you get your two critical points. Let's walk through that again. You start with your function. You want to find the local maximum minimum using the first derivative test. You start by finding the critical points. The critical points are where the function is 0 or undefined. Since the first derivative is a polynomial, it's just going to be where the first derivative is only going to come up to be 0, okay? So we take the first derivative, which is here, we simplify it, then what we do is we factor it out and set it equal to 0. When we factor it, we get this expression. And the solution is 9x minus 3 equals 0, which gives us x is equal to 1/3, and 2x plus 1 equals 0, which gives us x equals negative 1/2. And that gives us our two critical points. Okay? Alright, so I don't have enough time to finish this because there's 2 points over here. See if you can work this one. I'm gonna put it back here. This is a question. It's a good one. It's actually easier for the second derivative test on this one, but copy this down. See if you can work on it before next class, okay? And we have 1 minute left, so I'm going to stop. And I'm going to upload this lecture, so if you guys want to watch it on YouTube, I'll upload it now and I'll send it out. And